Now I started recording. Have you got the message?
Yes, sir.
Thank you. Yeah. So last time we have completed that LOM, okay, laminated object manufacturing technique. Now in this today's session, I'm going to start with your fused deposition modeling. Okay. So uh, start STAR size. Just a minute. Stratasys is the name of the company. Okay, Stratasys is the name of the company. This company was founded in the year 1989. Okay, and they have developed most of the company product based on that your fused deposition modeling. Okay, so before that particular this FDM technology, so that was developed by Scott. Okay, so in the year 1988, and they have started making use of this FDM in the year 1989. That is what I told you, and it got patented. Patent was registered in the year 1992. So FDM basically is going to use that extrusion process to build your three-dimensional models. Okay. So as I said that this Stratas, they introduced its first rapid prototyping machine, which is your 3D modeler, somewhere around 1992. And so from here, what I want to bring to your notice that fused deposition modeling is your extrusion based rapid prototyping process. What I said, that FDM is nothing but that is your extrusion based rapid prototyping process, and it works on the same your layer by layer principle which has been used in the other rapid prototyping systems. Okay, so in this fuse deposition modeling, so this also relies on your STL data file for the input, and this is capable of using the multiple build materials. Okay, this is capable for using your multiple build materials in build relationship, in your build relationship. So this is about the introduction of your this FDM, or the company who started using this FDM for the first time. So as far as the models and the specifications of the products which are being developed by that Stratatise is concerned. So they have developed a series of rapid prototyping machines, and it was the various machineries that they developed. So that was having the wide range of modeling materials to cater the different needs of the various types of industries. Okay. So this can be broadly classified into two categories: FDM series and the concept modeler. What I said, this particular company which started using this particular technology. Further, they have divided it into two categories. One is called as the FDM series. One is called as the FDM series, and the other one they call it as the concept modeler. Concept modeler. the FDM, typical your FDM series, so that includes the various models like your FDM. This is nothing but this is your FDM 3000 only, FDM 3000. Then that FDM maxim, the another name that they have given, that is FDM maxim. And there was one more this thing that is called as your FDM Titan. FDM Titan. Okay. And as far as that concept modular series is concerned, so this concept modular series that includes models like the dimensions and prodigy plus, dimensions and the prodigy plus. Okay. So again, in my subsequent slides, I have taken, this is the prodigy plus. Okay. And that comes from that this prodigy plus, so that is from that concept modular type. And this is was I was talking about just now, that FDM 3000, FDM maxim, and that FDM Titan, sorry. So later on we will go into details of this various machineries. Okay, the detailed specifications of this machineries that we will talk afterwards, after understanding the basic concept, the principle of operation and all. Okay. So before I go into detail of this machineries and all, so as I told you, this is your extrusion based rapid prototyping process. Okay. And as far as the last time, if you remember, I talked about the hardware, I talked about the software, then I talked about the build material. Okay. So uh, in this particular session also, I'm going to do the same thing in the same order. We will talk about, we'll discuss that FDM. Okay. We'll discuss about the same in the same manner. Uh, this is the basic principle which is used in this particular FDM technique. Here at the center, you can see that here that filament is there. Okay. And on either side, you can see that there are two driven wheels, and the this is the drive block assembly. So when you are going to rotate this drive wheels, so that is going to take that filament in a forward direction. And here you can see that in this particular, here that heating arrangement that is being made. So by applying that heat to your filament, that filament is taken in a forward direction with the help of that drive wheels, and then through that of your tip, that filament will come. And then as I told you, here that diameter of your filament that gets reduced. So that's the reason I used here the word that extrusion based rapid prototyping technique. And here at the bottom side, you can see over here that part is being built. So as I said, so this already we have seen there in the CAD CAM. Am I right? Can you recall this particular thing? We have learned it in CAD CAM. Hello?
Yes.
Yeah. So what I was telling to you, I was talking about, yeah, I was telling you that we will discuss first of all the hardware, then software, and then the build material. So this FDM system have evolved through the several models at the beginning with the original 3D modeler, with the original of your 3D modeler. And later on the various series got evolved, like here I have given you only one name, that is FDM 3000, which is used these days, or which is rather the popular. But at the beginning they came with the various series like 1500, 1600, 1650, then 2000, 8000. and quantum type of series. So basically that 50,000 to 2,000 models are capable of building. If you remember last time also I have given you the max dimensions of the components or the parts which can be built. So as far as the early in the early days, the FDM FDM 1500. So that or FDM your 2000. So that type of machine was capable of building that 10 by 10 by 10 inches ka part. Okay. On the other hand, if you see, just now I have taken one more name, that is that FDM 8000. So that FDM 8000 and the quantum, so that can build the parts which are of maximum size of 24 inches by 20 inches by your 24 inches. Okay. So this is about the this parts which are I mean key the dimensions of the parts which are been made using this type of your machines. Now this is about the hardware. This is about the hardware. Now regarding your software. So is this clear? Hello.
Yes, sir.
Yeah. So regarding the different softwares, let me tell you. So all these machines which are using this FDM 1500, yeah, FDM 2000 modelers. So they are using the powerful your quick slice software. The name of the software, just those who have the interest, let me tell you, they are using over here quick slice. That is the name of software which has been used over here, and it was developed by the that stratize only, and to manipulate and prepare the parts, they have again used that STL data files only for the use of your for the use in your FDM machines. Okay, so software you can operate on various types of your workstation. I mean ki right from your Unix to your PC based any workstation you can use, and also the modeler can be either operated directly from that workstation or by you can make use of any dummy computer whose sole purpose is to if you are using as I said the dummy computer, so the reason behind using this dummy PC is to free up the time and the space at your workstation. Okay, so this is about the softwares. I mean key in short that you have to remember that this name of the software which is called as the quick slice, and the type of files that we are using here, that is again a STL type of data files only we are using over here. Okay, so this is the main thing that you need to remember. The type of file, short form of the file will be your .stl file only. Now, regarding the material, so FDM can be equipped to build with the investment of your casting wax, then some material which is called as that ABS. ABS. So as far as that ABS is concerned, let me tell you what is the full form of this. This is nothing but this is your acrylonitrile. ACRYLONITRI, acrylonitrile butadiene. That's the reason it is called as ABS. That is called as. So this is a typical your plastic. This is the name of this a plastic. Then the medical grades ABS also you can use. Okay, there are some cases wherein you can make use of that medical grade wala plastic, which is mostly of a thermoplastic type, or any elastomers you can use. Um, that ABS that is typically been used on a large scale. Nowadays we are making use of that ABS as far as that FDM is concerned. So we are making use of that ABS instead of that elastomers and all. So the build and the support material that comes in the form of the filament, as I shown you here. So here in this particular form, that your build material will come. And as far as the diameter of this particular filament is concerned, so the typical diameter of this filament is somewhere around 0.07 inches. Okay, so as far as the diameter is concerned, the diameter of this filament is somewhere around 0.070. Okay, and that can be rolled on a spool. The typical the spool that you have to take, and over it is rolled like this. Okay, now the spool is mounted on this particular spool that has been mounted um, on a spindle at the rear side of this particular machine, and the filament been fed through a flexible tube attached. Okay, so there is a tube which is not shown here in this particular figure, but if you go to the back side of this particular machine right now, I don't have that particular picture. So but usually on the back side, if you view this particular machine from the back side, you will come to know that there the flexible tubes are attached on the back of this extrusion head. Okay, uh, now, just now I used word the extrusion head. So as far as that extrusion head is concerned, so that is the key element you can say in your FDM technology. So this head, this typical your extrusion head, that is very compact. It is a removable unit. You can detach it, and we are keeping it removable unit, because many a times we have to change for a change, we need to change it for the maintenance purpose, or some other material, good quality material suppose you got. So for that reason you have to use, you have to make sure that it is a removable unit. Okay, then it some I will not go into the much details of this particular extrusion head, but you just keep in mind as far as that extrusion head is concerned, so it is a crucial, it consists of so many crucial components, it consists of so many crucial components. Okay, now so this entire thing, that is nothing but that is your that is called as your extrusion head only. So this entire your figure that is showing your extrusion head only. This entire your figure, you can say this is nothing but this is your extrusion head. Okay, this is your extrusion head. Now in this extrusion head, now I will tell you something about this particular drive wheels. So this drive wheels, yeah, drive blocks are the raw material feeding mechanism. So you, as I told you earlier, that here from this particular figure also you can make out very clear key here. They are one of the wheel here that is rotating in a clockwise direction, the other wheel that is rotating in anti-clockwise direction. So um, this is a typical mechanism that we are using for feeding that raw material, and it is mounted on the back side of back of your head. Then the another thing that you can see over here, that is your drive blocks. Okay, so this drive block are computer controlled, and they are capable of precision loading and unloading of this particular filament. I mean, key loading and unloading of this particular filament, that will be taken care of by this drive block assembly. Okay, so it consists of two your parallel wheels, as I have shown you earlier, which are attached to the small electric motors through the gearing. Okay, and these wheels have the plastic or the rubber type of trading, and they are spaced. When I said that the this diameter of the filament is 0.07 inches, so that means you can easily say that the gap between these two wheels has to be the same, of range somewhere around 0.07 inches. And when these wheels are turning, when the wheels are turning and the end filament is placed between them, so they will continue to push or pull the material depending upon the direction of the rotation of this particular wheels. When loading filament is pushed horizontally, what I'm saying, ki when this particular filament that you are going to push it horizontally into the head through a hole of a little larger than the filament diameter, uh, so I'm talking about this, so which is the what you can say, the entry point, which is the entry point. Okay, uh, for to the heating chamber, which is the, I mean, key here also you can see why I said that, because here also you can see that key here the some heating filaments are also shown over here. Okay, now as far as that heating chamber is concerned, so that heating chamber, that you can see here that it has been curved through the 90 in the form of 90-degree elbow, where and the it is completely wrapped by that heating element. It is completely been wrapped by the heating element, which is going to serve that basic yeah, primary function of the heating. Okay, so one is to change the direction of that particular filament flow, so that the material gets extruded vertically in a downward direction. And the another thing, another important thing about this is that it is going to serve, it will serve as a melting area for the raw material or the for that filament. So heating element is you're basically electronically controlled, you can say, and it has some feedback thermocouples which are going to regulate, which are going to keep the or which are going to regulate the temperature throughout this working cycle. So heating elements are held at a temperature slightly above the melting point temperature of that filament ka material. And why we have to keep it above the temperature of that melting point temperature, why we have to keep that filament slightly above the melting point temperature of your filament ka material. The reason is simple. When you are passing that filament, when you are passing the filament from that exit of your chamber, it is in the semi molten state. It has to be in the semi molten state, and for that reason we have to keep the temperature of this filament slightly above the melting point temperature of this filament. Then and then only here at the end you will get it in a semi molten state. Am I clear? So this, or in other word, you can also say that this is going to allow this by keeping it slightly above, that smooth extrusion process and the tight control of your material, that is also possible. at the end of your heating chamber. Okay, and as far as the so this is about your this drive block assembly. This is about the drive block assembly. Now the another important thing here in the drive block assembly, that is nothing but that is your tip. So what you can see over here, the two tips are external. These are the two tips you can see over here, which are externally threaded, and I mean key. See here, uh, if you are going to, just a minute, I have to remove it from here then. Okay, so here this particular your tip you can thread on, or you can remove it. Okay, assemble and disassemble from this particular your entire drive block ka assembly, and for that purpose here you can see here the external threads are being provided. So the tips are externally threaded, and you can screw up into that heating chamber exit. Okay, that external, with the help of these external threads you can screw it up at the end of your heating chamber ka exit, and you can use it to reduce that extruded filament diameter to allow for a better detailed modeling. Okay, the tips are usually heated by that heating chamber, as I said earlier, to slightly above the melting point temperature of that material. Okay, the and you can easily remove, you can easily replace it with the different size of openings. The why we have to change that particular tip, just to make sure that what is the material which is coming out, what is the size, or what is the opening of that particular tip, that matters a lot. So depending upon the different size, you can use the various tips. Usually this particular size or this particular diameter is of the range 0.012 to 0.025 inches. Okay, so in this particular range you will get the various tips. Is it clear?
Yes, sir.
Yeah. So as far as this FDM modeling operation is concerned, so before as I told you earlier, before building any part, you need what? You need that STL file. Okay, and that STL file has to be converted into some machine language, which has been understood by this particular your FDM machine, which is understood by your FDM machine. And as I told you earlier, the typical your this thing, that software which is named as quick slice. Okay, which is named as your quick slice. So that software is used for this particular purpose. I mean, for making to make that machine to understand that STL file. We are making use of that quick slice software. That is what you can say. So this STL file is read into that quick slice, and it has been displayed graphically on the screen in the Cartesian coordinate system along that x-axis, y-axis, and that of your z-axis, and it has been shown in a typical bounding box. Okay, various, I don't have the figure right now with me, but you can say that a typical bounding box you can see, and that quick slice software that gives you the option on that FDM system uh, used to be used. Okay, I mean whether that slice layer, how to control the slice layer ka thickness, or how to use that build and support materials. So all those things that you can control. Not only that, the another important thing, that is the tip size. Okay, so that also you can control by making use of this particular software. Okay, that is called as your quick slice. Okay, is it clear?
Yes, sir.
Yeah. Now, regarding the part size and all, so as far as the part size is concerned, so that part will fit into the bounding boxes. Okay, and if it is unable to fit it into that bounding box, so it will either have to be scaled down to, so that you can fit it there, you can fit it there in that bounding box. Okay, so usually the I mean it has been suggested that for a designer to add some alignment bosses, or some slots are added, so that the proper alignment of the subsections can be easily achieved with the help of this particular system. Okay. Now, if you remember, uh, now before we go into this detail, let me tell you. So as far as from this particular discussion, now what you understood, as far as the working principle of your FDM is concerned. Okay, so it is based on the use, how efficiently, how effectively you are making use of that heat energy or the thermal energy, and you can build, you can develop the model by in the layer by layer form. Okay, so the material which is there in the form of filament, so that is wound around your spool, and that has been melted by using that typical heads which I have shown you just now, and that tips which are there at the ends of that particular heads, so that is going to extrude that particular filament. Okay, and as it has been extruded, as that filament comes out of those heads, I mean it has been cooled, and thus it gets solidified. That molten metal which is coming out of that particular head, or which is coming out of that tip, so that need to be solidified. So for that you have to cool it, and after putting it on the table, so that cooling is done, and thus that typical model that we are going to build in a layer by layer form. Okay, so it is similar to the other I mean in the other your rapid prototyping techniques also, we are building the usually the materials in a layer by layer form. So in the same way here also we are doing it, here also we are doing it the same way. So from this particular discussion, what you understood as far as the different parameters which are going to affect the performance, the functionality of your system, these are nothing but the what is the strength of your that raw material, I mean the filament ka material, then the it's like how flexible it is, or rather the flexural modulus, then as with the help of your heat, you are melting it, or you are getting it in the molten state, and then further for developing a proper model, okay, that viscosity of that raw material in the molten state, or that viscosity of the raw material, that is also important, okay. um, then the other thing, that is the what is the width, what is the deposition ka speed, then what is the volumetric flow rate. So all those things that are typically governed by this particular tip. I mean ki the deposition ka speed, that a volumetric flow rate, then the size or the diameter of that extruded filament. So all those things that depends on the tip ka dimensions and the tip ka hardware, okay. So for that reason, that a tip is very important, okay. Tip is very important. So that this is about the basic things that I wanted to discuss with you. Um, what is the time right now? Anything else you want me to ask? Whatever we have discussed till now, based on that, if you have any doubt, you unmute yourself and you can ask me. Bachalo. Hello.
Yes, sir.
Yeah, I'm saying to you, do you have any doubts? Hello.
Hello.
Yes. Tell me.
Sir, am I audible?
Ha, now you are audible. Tell me.
सर अगर LOM और FTM में अगर टाइम का कंपैरिजन करें तो मतलब कोई भी एक प्रोडक्ट को बनाना है उसके लिए मतलब सेम
Ha.
प्रोडक्ट को बनाना है और मेथड अलग-अलग यूज़ किया ये तो
Ha.
सर
Nah,
मतलब
nah. You mean to say which is more faster?
यस सर
Time where you can save more time. See, this particular technique, which one? FDM ka speed. So that is comparatively lesser, okay, in comparison to your LOM. Again, it depends on what? It depends on what is the overall dimensions of the part which you are going to make using using this particular technique, whether what is the final dimensions, overall width, overall height, overall diameter. So all those things matters a lot. But if you prepare both the components by using LOM and by using the FDM, so in that particular case, you will found that the components which are being made by using your LOM, so are more faster. Why you will found it so? Because there what is happening there, already you are taking that particular raw material in the form of the sheets only, and you are cutting those sheets and you are going to paste it one sheet above the other, okay. In this particular case, what is happening that after, even though the final product is made, okay, but again you have to allow enough amount of time so that it becomes a solidified. In that particular case, that will not be the issue, because already there the that material is in the form of the sheets only, and only the heat that you are using, heat you are applying, that is only for cutting that particular sheet. So there the amount of time that is needed for the proper I mean after building the height, or the after building the component in the Z direction, then the amount of time needed for cooling down or for solidifying, so that will be more in case of the components which are made using your FDM, and in case of your LOM you will found that time is less, comparatively lesser. Okay.
Yes, sir.
Yeah. Anything else? If not, then I would like to stop it here. And in the next class, then I will discuss, I will take this particular topic ahead, and how that slicing is done. Then what are the advantages, what are the disadvantages, what are the typical applications, and the typical examples of the various parts which are been developed at the beginning and all. So that I will discuss in the next session. Also, the another thing which I told you, that is this particular information regarding the specifications of various machines. So that also we will discuss in the next session. Okay. Here also you can see, this is what I was talking about, that quick slice, then the material which was your ABS. I have already discussed this particular thing with you. I talked about this material, I talked about the software. There is one more software which is called as the Insight, but most widely popular software, that is your quick slice only. And here you can see the various dimensions, okay, width, height, depth, then the typical weight is given. The numbers which are there in the bracket, so that tells you the weight in the pounds, okay. The typical your accuracy level, tolerance ka value, so that are also given over here. Okay. Okay. So I will stop here, and then we'll continue rest of the thing in the next session. Just a minute.